Good morning. Today we will continue our consideration of a process that is called skew Brownian motion. So we have a process in one-dimensional Euclidean space, and diffusion coefficient is supposed to be equal to 1, and denoted by GTXY. Transition probability density of Brownian motion. And we are going to perturb this process by the following vector field, not in this case, maybe by the following drift coefficient. A of x equals q delta x. We will write down R instead of R1, okay? So Q is a real constant, and delta x is a Dirac's delta function. It means that it acts on a test function by the following rule. Phi, this is the value of this function at the point 0, x being equal 0, okay? Now, if we write down formally the corresponding Kolmogorov backward equation, in this case it can be written as follows: du dt minus 1/2 d2 u dt square equals 0. Okay, and if we are going to write down here an additional term.
Excuse me, shouldn't it be dx? The second
Yes. Thank you. Dx squared. If we are going to write down here minus q delta x du dx, so you see in this equation this delta function must be compensated by some term, and that may be only the second derivative. Okay, but if the second derivative gives us delta function, then the first derivative must be discontinuous, must have a jump at that point. So we have multiply delta function by discontinuous function. If, let us think about the following thing. If I have some generalized function, I know the rule how it acts on a test function, okay? And let us ask ourselves, what a function psi must be a multiplicator for this generalized function. What a function psi. It is easily to comprehend that psi must be such that the following action makes sense, okay? So if I generalize Dirac's delta function in the following way, phi 0 plus phi 0 minus. So this function is such that it has the limits, this one and this one, okay? So then I can, according to this, I can, this function with the jump at the point 0 can be a multiplicator for this function, okay? Now let us recall the following equation for the transition probability density of a perturbed process with this drift coefficient. So we have the following equation: gtxy plus integral g tau x z a of z d g t minus tau z y dz. Okay? And now I am going to use this rule, okay? We have here delta function, Dirac's delta function, maybe this generalization. This function is continuous. So, and you can guess that this function is not discontinuous. It exactly jumps at the origin. Okay, so I would like to write down here the sum. Let us denote that sum Vt minus tau y. This is 1/2 dgt minus tau z y dz, z being equal to 0 minus plus dg t minus tau z y dz z equals 0 plus. So I can write here q integral from 0 to t d tau integral g tau x 0 v t minus tau z not z y d tau. Oh, excuse me. I am sorry. That integral that integral vanishes. Okay, so d tau. Okay, instead of this. These two integrals, I can write down here only one integral using this rule. So we have the following formula: g t x y equals g small t x y plus this expression. Okay. And now let us look at the kernel of this integral operator. It is the following function: e to the power minus x squared over 2 tau. You see, if x is other than 0, then this function has no singularity at 0. Okay? If x is other than 0, then this function goes to 0 as tau goes to 0 much faster than any power of tau in the denominator. Okay, so I can differentiate this function at any point x being other than 0. Let us differentiate. So if x is other than 0, we can write down dg dx tx y equals dg tx y dx plus q minus q integral from 0 to t 1 over 2 x over 2 pi tau cube e to the power minus x squared over 2 tau v t minus tau y d tau. And now let us consider this kernel. Let us calculate full mass of this function. So I should calculate such an integral x over 2 pi tau cube e to the power minus x square over 2 tau d tau. We make here the change of the variable tau okay, then tau to the power minus 3 over 2 equals 2s over x squared to the power 3 over 2, okay, and d tau equals minus x squared over 2s squared ds. So this integral is equal to, if tau equals 0, so s is equals infinity, plus infinity, and here x squared over 2t, okay, minus I have already taken into account, okay. Now we have here x over 2 pi, now this one, 2s to the power 3 over 2, x squared to the power 3 over 2, and d tau x squared 2s squared ds. And you see we have here x cubed over x squared to the power 3 over 2. What is it?
One.
No. Signum x. Signum x. Okay? Because you see, square root of x squared is absolute value of x. Okay. So we have here signum x integral from x squared over 2t to infinity e to the power minus s to the power minus 1/2 ds. And if x goes to 0, if x goes to 0 plus minus, okay, here we have gamma in the limit gamma 1/2. This is exactly square root of pi. We have that this limit is equal to plus minus 1. Okay? And moreover, if I consider this integral of this function from delta to t let delta be positive and less than t of this function. So we have here instead infinity. Here we have x squared over 2 delta. Okay? And it is evident that if x goes to 0, this goes to 0. So this goes to 0 if x goes to 0 plus minus. What does it mean? You see, the full mass goes to plus minus 1, and if it means that this function is something like delta, Dirac delta function in the limit. Okay? So if I have here, and that delta function is concentrated at the point tau being equal to 0. So the limit of this expression as x goes to 0 plus minus will be the following one: plus minus minus plus q v t 1 tau goes to 0 if v is continuous function, if v, so let us formulate the function v must be such that v of tau y is a parameter. So as a function of tau, it must be continuous for all tau positive. T is fixed here and positive. Okay? And it must be integrable at the point 0. So if for some epsilon, okay, if it is integrable and continuous, we have this there in this formula. Everything is okay, and we have that limit of as x goes to 0 plus minus dg dx tx y equals, here we have y minus x, or so we have x to 0 y over 2 pi t cube e to the power minus y squared over 2t. Okay? But let us recall that v is 1/2 of the sum of these limits. Okay? So if I add we have here two equalities. If I add them, I can find out v, the function v. Okay, so v t y equals y e to the power minus y square over 2t square root 2 pi t cube. Okay, and now let us substitute this function into this formula. We get the following formula for G capital T X Y.
Excuse me. Can you please explain once more how we got V?
V, by the definition, V T Y were 1/2 d G T X Y, dx x equals 0 plus dg tx y dx if x equals 0 minus. Okay, and here we have dg plus and dg minus. I add both these equalities, and here we have v. This is
Pencils on.
yes, and we have this formula.
I can think you're
Okay, so we have the following integral from 0 to t. Let us write down here e to the power minus x square over 2 tau square root to 2 pi tau, and here y e to the power minus y square over 2t minus tau over square root 2 pi t minus tau cube d tau. And now we calculate this integral. It can be calculated in an explicit form.
So we at first assume that a solution exists and satisfies some equation with generalized
Yes,
degree,
yes.
and then make some formal calculation, and if a solution is nice,
Yes,
then we have this, and then we will check then,
yes, yes. So this is not a finish.
yeah, this is a guess, nice guess
Yes,
of
yes,
density.
This is heuristic
Calculation.
reasoning. Heuristic. Okay. So this integral, how to calculate this integral? I have already proposed you to prove the following formula. integral from 0 to infinity e to the power minus pt e to the power minus x squared over 2t dt. In the book by Ito and McKean, this is an exercise, and there is some hint how to calculate this. They proposed calculate this integral with the help of integration in complex plane. In a complex plane, and they indicated the contour along to which you should integrate. And it was very long ago, I made that. And the following formula is true. This is, here x is a real number and p is such that it may be complex, but real part of p must be positive. Okay? So the formula is as follows. This is over 2p e to the power absolute value of x square root of 2p. Okay? And now, if x is other than 0, we can differentiate both sides of this formula, and we arrive at the following formula: e to the power minus pt x. Oh, excuse me, I forgot here, write down, I am sorry, 2 pi t. Sorry. Square root of 2 pi t. Okay, so let us differentiate with respect to x. X to the power minus x squared over 2t square root 2 pi t cube dt equals signum x e to the power minus x square root of 2 pi. Now, let us look at this integral. This integral is nothing else but the convolution of these two functions. So, if I take Laplace, this is the Laplace transform of this function, yes? If I take Laplace transform of this integral, I obtain the product of Laplace transform of this function and this one. Okay, so this one, it has the following: Laplace transform minus absolute value of x square root 2 pi over square root 2 pi, 2p, p, sorry. And this one, sigma y, not sigma y, e to the power minus y square root of 2p. So we can write down what this integral is. So g t x y equals, let us write down 1 square root of 2 pi t x minus y minus x square over 2t plus q sine y, okay, square root over 2 pi t I have already written, and here we have x minus absolute value of x plus absolute value of y square over 2t so we have an explicit formula for the transition probability density of the process desired. But as was mentioned, these were only heuristic reasoning. Okay? And now we have to verify that this is indeed a transition probability density of a Markov process. Let us see that g t x 0 plus minus is equal to 1 plus minus q over 2 pi t e to the power minus x square over 2t. So this function as a function of the third argument is discontinuous. Okay? So it is discontinuous. But if we look through those arguments, you will see that they remains to be true if we believe that sign 0 is 0. So this function is discontinuous, but let us set that gtx 0 equals gtx 0. Okay, so we have the following. We have to verify the following properties of this function. It satisfies the Kolmogorov-Chapman equation for any q. For any real q, it satisfies the Kolmogorov-Chapman equation. Its full mass, that is integral over r g t x y dy, equals 1. And now you see, if q is less than, absolute value of q is less than or equal to 1, so we have here the following fact. This function takes only non-negative values, because this is always less than or equal to y minus x squared. This squared. Okay. So it is indeed transition probability density. And now we should verify, is it a diffusion in Kolmogorov sense or not? But now is time to make a little break. Let us continue. So we have to testify, is this process a diffusion in the sense of Kolmogorov or not? So we have the following estimate for g, t, x, y. It is less than 1 plus absolute value of q e to the power minus y minus x squared over 2t over 2 pi t. And this estimation shows that there exists a continuous Markov process with this transition probability density, because you remember that if I have some transition probability density that satisfies the following inequality. Then there exists a continuous Markov process with this transition probability density. This criterion of the existence of continuous Markov processes was proved in 1952 by Dynkin and in 1953 by Kinney independently. Okay, so we have this very easy. So let us calculate the following. And this means that the first condition in the definition of diffusion process in the Kolmogorov sense is fulfilled the first, because that condition was this dtx y dy goes to 0 as t goes to 0. Okay, and from this we have. Okay, now we have to calculate and y minus x squared g t x y dy. This is not difficult calculations, and I know that I have already made those calculations, and the following formula is true for this. Q integral from 0 to t e to the power minus x squared of 2 tau d tau over square root 2 pi tau, and this is equal t minus 2 q x integral, the same integral, 2 tau d tau over 2 pi tau. Okay, you see, let us consider the second equality. If I divide it by t, I will have here 1 minus 2 q x over t integral e to the power minus x squared over 2 tau d tau over square root 2 pi tau. If x is equals 0, so we have that this limit is equal to 1. Even not limit, but for x being equal to 0, this equal to 1, okay? But if x is other than 0, then this function is, as tau goes to 0 very fast, okay? So this integral must be convergent to the value of this function at the point tau being equal to 0. But that value is 0. So this divided by t goes to 1 as t goes to 0 at any point x. So the third condition in Kolmogorov's definition is fulfilled. At any point x, we have that this limit equals 1. And what about this? If I divide it by t, so you see, if x is other than 0, we have here 0. Okay? The same reason. We have here 0. But if x equals 0, then we have here signum q infinity plus infinity multiplied by plus infinity if x equals 0. So if q equals 0, our process is nothing else but Brownian motion. But if q is other than 0, we have that at the point x, at the origin, this limit does not exist. Okay? So it is not a diffusion in Kolmogorov sense. Only one point, namely origin, is such that the condition, Kolmogorov's condition, does not fulfill. And you see, this behavior is like delta function. Delta function is also equal to 0 everywhere except for origin. And it is not difficult to verify that this is true, that that function has as its limit Dirac's delta function. So if I integrate some continuous function compactly supported with that it will be q integral q over t integral phi of x e to the power minus x square over 2 tau dx square root 2 pi tau And here we have integral phi of x square root tau e to the power minus square root x square root 2 pi dx. And here one more integral d tau. You see, if tau goes to 0, so this goes to phi of 0 q. So exactly this function you may assert that this function converges to q
how do you transform the first integral into the second one?
here.
Yes.
I use this formula.
Ah, okay.
Okay. So this is an example of a generalized diffusion process that is not diffusion in Kolmogorov sense, but in some generalized sense. It is a diffusion, and this is its drift. And what an interpretation of such a process can be given? What does it mean? I propose the following interpretation. For this process, there is a membrane at the point x being equal 0, at the origin. Is a membrane. So it does not influence our process if it walks somewhere on the distance of this point. Then this drift is equal to 0. So this is a Brownian motion at any point other than 0. But at the point, at the origin, it receives some impulse or pulse, such that trajectory remains to be continuous, but the probability, if we reach this point and then start from it, so the probability that at any instant of time our process takes on positive value is 1 plus q over 2. And the probability that xt is less than 0 equals 1 minus q over 2. So this point becomes non-symmetric. Okay. So I would like to finish considering skew Brownian motion. But only one question I would like to ask. You see, this function satisfies the Kolmogorov-Chapman equation for any q, for any real q. It is non-negative for q, for such a q, the absolute value of q is not greater than 1. And the mass of this function, the full mass, is equal to 1. So it is transition probability density of an object that is called pseudo-process. And for me, the following question is very interesting. Is there or not in the nature, or maybe in social life, such phenomenon that that is evolving according to this transition probability density?
For q greater than 1.
Yes, for q greater than 1. Absolute value of q greater than 1. I do not know the answer to this question. Okay, and I would like to write down one more formula and briefly discuss what it is. Now let D be greater than 1 and G T X Y is transition probability density for Brownian motion in RD and let nu be a unit vector in RD and let S be a hyperplane that is orthogonal to mu. And the following, I would like like to write down the following formula: g t x y plus integral over s g tau x z y nu t minus tau g t minus tau z y. Oh, I forgot to define a function. Let a function q of x on this hyperplane be given such that it is continuous and takes on its value from the interval -1, 1. So I would like to write down here q of z d sigma z. So this inner integral is a surface integral d sigma z. Z indicates argument with respect to integration. We integrate here, okay? Z. This surface integral is very simple because S is d-1 dimensional subspace of Rg. So this is integral with respect to the Lebesgue measure in this d-1 dimensional space. Okay, and this here we have the derivative in the direction nu d nu z g t minus tau z y if z is a point from S. So what is this derivative? We have nu multiplied by y by nabla z of this function, and that nabla is equal to y minus z over t minus tau g t minus tau z y. And if z maybe this bracket maybe here can be written appear.
So should it be small g or capital G in the right hand side under the integral? So
G small.
So this is not the equation.
Not this.
So
is,
let us consider
yes.
this function.
But it can be obtained, this formula, by the arguments like we obtain the formula for skew Brownian motion. If the surface is not hyperplane, then we have some integral equation to be solved. It is possible, but the explicit formula, this is an explicit formula for G. capital is into quadrature, is into quadrature. Okay? So if z belongs to S, z mu is equal to 0, so we have here exactly d mu z. Okay? And you can consider it as an exercise. Try to verify that this is transition probability density. So it satisfies the Kolmogorov-Chapman equation. Its values are non-negative under this condition. Full mass is equal to 1, and it is not a diffusion in Kolmogorov sense, but it is a generalized diffusion. So if we consider integral y minus x theta g t x y dy as t goes to 0, it goes to nu theta q of x delta s of x. Where delta s of x is such a function that it acts on a test function according to the following rule. This is a surface integral over s phi of x d sigma x. Okay, and b, so we can multiply this by phi of x, integrate, and here we have this fraction, this q of x, phi of x. Okay, and in the same sense, b y minus x theta square g t x y dy goes, as t goes to 0, goes to theta square. In the same sense, if I multiply this by phi of x, so I obtain that. So this is some multi-dimensional generalization of a skew Brownian motion. And again, what interpretation of such approaches can be given? So we have this delta function is equal to 0 outside of our hyperplane. Okay, So there is no influence on the motion of our particle when it is on some distance, on some positive distance from S. But if it visit this hyperplane, it receives some pulse, okay, but such that this process is continuous. The very easy the following estimation can be obtained. One plus norm Q G T X Y. By the way, from such an equality 1 minus norm Q G T X Y. Okay, so these processes and someone for S being not a hyperplane but a curved surface, such processes were constructed, and you can find details of those constructions in my book that is called Generalized Diffusion Processes. I have already mentioned it. So I was told yesterday that this is my last lesson during this semester. So I thank you to every one of my listeners, and bye.
Recording
Я
stopped.
хотів сказати, ну ладно.
Ще вот эти.
I must organize something like exam, and my proposition is June 13 or 14 this time, 9.
We have 15 June rules, I think so. Maybe a little bit later.
18?
18, 19.
Oh, yeah, okay. Okay, as you like. Maybe we